our whole goal for the chapter was to be able to give an individual electron an address, right? We want to know where we can find a particular electron. And so we worked out the arrangement of atoms kind of in big groups with electron configuration and orbital notation. And now we're going to look at something called the quantum model. And that allows us to give individual electrons an address. Okay, so that's really our goal. We're getting into the last step of chapter 4 here. Okay, so this slide, sorry, it's a little funny on mine. I think it printed better on yours, maybe. I'm not sure, but the quantum model is about basically having all of these shapes of orbitals like we talked about, and they essentially form this electron cloud, right? And so when we put all the shapes together, we said they don't have really defined lines. They have a probability of being found within that shape. And so it makes kind of this electron cloud. Okay, so the quantum model says the probability of finding an electron in a cloud surrounding the nucleus is proportional to the density of the cloud, which means the closer to the nucleus we are, the more likely we are to be able to locate an electron. Okay, the quantum number specifies all of the different parts of the address of the orbital. It tells us what energy level it's in. It tells us what shape of orbital it's in, what version of that orbital, and then it tells us if it's the first one to go in or the second one. So it tells us a lot of information. And so when we talk about the quantum number, there are 4 parts to the quantum number. Okay, I don't really want to even say 4 quantum numbers. I want to say it has 4 parts to the quantum number. Okay, there are 4 parts to the quantum number. And so essentially just like your address has 4 parts, right? Your address has 4 parts because you have your house number. What else? Your street, then city, state, then zip code, right? Your address has 4 parts to it. So just like that, our address of our electrons have 4 parts to it. Okay, typically a quantum number is listed like this. It's given in parentheses with 4 numbers following it. Okay, it's given in this kind of format just like this. Okay, so that's really what we're talking about. When we say quantum number, we mean this 4-part address. So the quantum number is not just 6 or 25, right? A quantum number has all 4 parts. It's the address for the electron. And so we're going to figure out, how do we determine the quantum number? How do we find out that address? Okay, so we said there are 4 parts to them, and we're going to go through each of these individually, but we'll just kind of do an overview. The first part tells us the main energy level of the electron. So if my electron is in a 3p orbital, that means that the energy level is a 3, right? That's how we find that. If it was in a 4d orbital, what would my main energy level be? 4, right here. Okay, so that's how we find out what energy level we're in. We look at what orbital we're in. The second tells us the shape of the orbital, and so we're going to look at how we can give a number to that shape. Third one tells us the orientation or the version of the orbital. And the last one tells us what's called the spin state. And so that's what we talked about yesterday. 1 electron spins in the positive direction, 1 electron spins in the negative direction. We're going to be able to differentiate that within the address itself. Okay, so there's 4 parts. We're going to start looking at each of those 4 parts individually. The first part tells us we have a name for each of the 4 parts of our address. I'm not really concerned with you knowing the name of the individual parts, right? We just need to know that a quantum number takes up 4 parts, and we have those things, okay? So the first part of the quantum number gives us, we said, the main energy level of the electron. The values for that can be it can be 1 through 7. We can never have an energy level of 0, right? So our quantum number will never start with a 0 because there's no 0s orbital or 0p or 0, you know what I'm saying? There's no energy level that's 0. So it will never start with a 0. It would start with a 1, or we could go all the way through 7. 7s is our biggest right here. Okay, so the first part of our quantum number can be 1 through 7, and it's just dependent upon whether or not, it's dependent upon what energy level we're in. So let's go ahead and build, let's use rubidium as our example for right now. If I'm looking at the last electron in rubidium, number 37, what type of orbital would it be in? Rubidium's configuration would end in what? 5s. Rubidium would be 5s. And so the quantum number for rubidium would start with a 5. Right? And that's all we know so far is the main energy level. Are we on the same page with that? Okay. That's all we can do so far because that's the only part of the quantum number we've learned is the energy level part. Okay. If I were going to do platinum, number 78, how would its quantum number start? With what number? Tell me, how does its configuration end? 1, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. 5D. And so its quantum number would start with a 5 also. Are we okay with that part so far? Okay, so let's move into part 2 of our quantum number. Okay, this tells us the shape of the orbital. The shape of the orbital. Okay, I don't need you to know the name of it, angular, quantum, I don't care about that. Okay, you need to know what it represents. So this tells us the shape of the orbital. Okay, I'm going to give you a little table here that tells us what our shapes are. Okay, so on the next slide, you can see this. This tells us our quantum number part. It's given with an L. I don't really need you to know that so much, but the second part of our quantum number is designated as an L. This tells us that if it's in an s orbital, the numerical value assigned to that is 0. If it's in a p orbital, the numerical value is 1, d orbital, and f orbital. So I just do this with my hand, right? I just literally go s, p, d, f. Okay, S is 0, P, D, and F. Okay, so when I'm trying to build my quantum numbers, I still do it now, even when I'm working on problems, right? It's S, P, D, and F. Okay, so let's go back to our previous example where we looked at rubidium. Rubidium, we said, was 5s. And so the quantum number for rubidium would start out with a 5. And then the shape of the orbital is S. So what numerical value goes with S? 0. So those are the first 2 parts of our quantum number. Okay, are we doing okay so far? The other example, what did we give? Was the other platinum? Was 5D. And so it started out with a 5. And then what numerical value goes with a D orbital? S, P, D. So it was B2. Okay, are we feeling okay with that? We need to understand that when we talk about an element like this, it goes without saying that we're studying the last electron to go in that element. So for rubidium, we're studying electron number 37 specifically, the very last one to go in rubidium. Because if I studied electron number 19 in rubidium, I need you guys to hear this because this is important. If I studied the 19th electron to go in rubidium, it would look just like potassium. Right? Because the electrons go in the same order for every single element. They get put in at the same order. The first 2 electrons go 1s, the next 2 electrons go 2s, 2p, 3s, 3p, right? They fill in the same order regardless of what atom we're looking at. And so if I wanted to examine the 12th electron to fit into rubidium, it would be just like I was looking at magnesium. Okay, does that kind of make sense? Our electrons fill the same order regardless of what atom we're looking at. So I could ask you, what's the quantum number of rubidium's 4th electron? And you would say, well, its 4th electron would look just like beryllium, which is 2s2, and I would give the quantum number that goes with that. Okay, so we can give every single electron an address. But when we talk about we're giving the quantum number for platinum, that means we assume it's its last electron. So for platinum, it would be electron number 78 would be the one that we would be giving the address for. Okay, is that kind of clear? Okay. So S, P, D, F. Do you have a question, or are you still just percolating? Let's keep going and put them all together, and then we'll see if we still have questions. Okay, that's fine. All right, the third part of our quantum number. I don't want to do this one. For the third part of our quantum number, again, they give each of them a letter like designation. I don't need you to know that. Okay, I don't. So I need you to know how to solve it, basically. The third quantum number tells us the orientation or the version of the orbital around the nucleus. Okay, so this really applies after the s orbitals, but let's look at what I'm talking about here, okay? If I have an s orbital, 1s, I just drew it as a single line, right? Do you remember that? Because there's only one version per energy level of s orbitals. But for p orbitals, let's say I'm drawing a 2p orbital, we said there are 3 versions of p orbitals, aren't there? And so now with this part of our quantum number, we're going to tell which version, this one, or this one, is that electron fitting into. Okay? In all reality, these versions of our electrons fit around the nucleus in different ways. One on the x-axis, one on the y-axis, and one on the z-axis, right? They fit around that nucleus differently. So we're going to tell what version of the orbital it's in. Okay? And so here's how we do that. Let's start with our platinum example because it's a d orbital, okay? So let's go to an example. And we've been looking at platinum so far, PT. We said it is 5D, 1, 2, 3, 4, 5, 6, 7, 8, okay? 5D8. And so far, we know its quantum number is 5, 2. Would we agree with that? Okay, so now to find the last 2 parts of the quantum number, we need to draw its orbital notation. Just the last part of it. Just the last part. So what we learned yesterday with the arrows and drawing the orbital notation, we need to draw that to help us with the address, the last 2 parts, okay? So 5D8, we're going to put in our electrons. 1, 2, 3, 4, 5, 6, 7, 8, right? Remember how we fill them across and then we put in our second one? Are we agree so far? Okay, so once we do that, once we show that, we're trying to examine the 8th electron we put in, which happens to be this one. Would we agree? The last electron we put in is that electron, number 8. So now I've got to tell what version of the orbital it's on. Okay, and here's how we do that. We label our orbitals starting with a 0 and working outwards like a number line. Okay, we start in the middle, the very middle version of our orbital with a 0, and we label them outward like a number line. So you'll see that it's a d orbital, so its number is 2. The next range is negative that to positive that. Okay, we'll look at that in more examples. But we start in the middle with a 0, and we label outward like a number line. Yeah, go ahead. This is the version of my orbital it's on right here. Would we agree? So the next part of my quantum number tells me what version of the orbital it's on. Okay, and so since this is labeled with a 0, the next part of my quantum number is a 0. Okay, I know this seems like a lot, but we're going to get lots of practice in with it, okay? The very last part of my quantum number is the easiest one. Yeah, okay, sorry, go ahead, Hannah.
What about S's?
Yeah, that's a good question. So in an s orbital, there's only one version of that orbital, right? So if in my example that we gave with rubidium, 5s, and then it automatically has to be a 0 because there's only one version of it. So we still start in the middle with a 0. So if it's an s orbital, it's always going to go 0, 0 in the middle, right? Always. It would always go 0, 0. That's a good question. Okay, the last part of our quantum number, I'll skip to the slide here in just a second, but the last part of our quantum number is the easiest one. And for some reason, it's a half. It's a +1/2 or a -1/2. Those are your only 2 options to put in there. So I'm going to look at this electron I'm examining. And is it the first one to go in or the second one to go in? It's the second one that I put in because it's facing downward, isn't it? It's facing in the negative direction. And so our last option is only -1/2. Okay, the last part of our quantum number only has two choices. +1/2 if it were pointing upward, or -1/2 if it's pointing downward. And so this electron is the second one to go in, which means it's spinning in the negative direction. So it's a -1/2. Okay. Let's go back and look at our rubidium example. Rubidium we said was 5s1. So I'm examining this electron right here. 500. Would it be a +1/2 or a -1/2? A +1/2. Because it's the first electron to be placed in the orbital. Right? And that's pointing upward. Okay, so I know that's a lot, right? I gave you a lot of information and a lot of rules all at one time. But the important part of it is really going to be that drawing and helping us figure out what version and if it's the first or second electron to go in. So we need to feel pretty comfortable with our orbital diagrams. Okay. Let's look at the last, this is the slide for that last part. The fourth part of our quantum number only has two possible values, +1/2 or -1/2. And so it tells us, is it the first one to go in or the second one to go in? Okay, and so if it's the first, it's pointing upward, which means it would be positive. And if it's the second, it's pointing downward, which means it would be negative. Okay. So we're going to do just a whole bunch of examples now. I think that maybe is the last slide that I printed for you. Is that true? Okay, so we're just going to do a bunch of examples now with quantum numbers. Okay, so let's give yourself some room and we're going to do some examples here. Okay, let's start with nitrogen. Okay, since I know I'm going to need it, I like to just go ahead and start by drawing the last part of nitrogen's orbital notation. So nitrogen ends with what? 2p3, I would agree. So I'm going to go ahead and draw out that 2p orbital. I know I'm going to need it eventually. So I'm going to go ahead and draw out that 2p orbital and I'm going to put in my electrons. So do I put in my electrons like this? 1, 2, 3? No, I fill them across all the way. So 1, 2, 3. And so if I want to know the quantum number for nitrogen's last electron, which one am I examining? 1, 2, or 3?
3.
Okay, so I like to circle that one. So I kind of focus in on this is the one I'm looking at. Okay. I know that I'm going to need to label my orbitals. So I'm going to go ahead and do that. 0, 1, -1. Okay, so I've kind of done all of my prep work now, right? I've given myself a diagram and a visual of this electron. And so now let's go ahead and give it its address. Okay, so we're going to start our quantum number with what the energy level. So that is what? 2. Okay, now I need my shape. So I'm going to go S, P, D, F. So what numerical value goes with P? 1, right? S, P, D, F. So I've done 2P. Now the third part tells me what?
Oh.
What do you think?
The shape.
Not the shape. We already did shape.
The orbital.
Yep. Well, kind of, yep. Level, shape, version. Okay, the version of the orbital. So that is in this case, a 1. Okay, so this tells me version. And then our last part, it's just +1/2 or -1/2. So what's it going to be here? +1/2. And that's it. That's our address. This gives us the address for the 7th electron in nitrogen, the last one to go in. Does that feel a little bit better once we have all 4 parts at once?
Yeah.
Okay. We ready to try another one?
Do I need to put the little addition sign by the one?
Yeah, it is preferable if you put a +1/2. Don't just leave it as 1/2, right? That's kind of a standard practice. Okay, let's try copper. Cu. I want the quantum number for the last electron in copper. Okay, and so copper, I think, is 3D9. I would agree. Do we agree that copper is 3D9? So we're going to be in the 3D, and then we count over. It's the 9th one, so 3D9. So again, I'm going to go ahead and draw my 3D orbitals. Why do I have 5 different versions of my 3D orbitals? How many can it hold?
2.
Okay, each orbital can hold 2, but how many electrons total do we need to fit in the d orbitals?
10.
Okay, so here's how we remember that. There are 10 spots across the d orbital. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And each orbital can only hold 2 electrons. So 10 divided by 2 tells me I need 5 versions of that. Yeah, Noah? Say it again. So that's just a standard rule for any orbital can only hold 2 electrons. That's why we only draw a maximum of 2 electrons per line, right? So any orbital can only hold 2 electrons. Okay, so let's go ahead and put our electrons in. 1, 2, 3, 4, 5, 6, 7, 8, 9. And so I'm examining which electron? The very last one I put in, right? That's the one I'm looking at. I'm going to go ahead and label my orbitals 0, 1, 2, -1, and -2. So I've done all my prep work. Now let's go ahead and give it a quantum number. Okay, what will its main energy level be? 3, because it's in 3D. So 3. Then it's a D shape. S, P, D. 2. Which version does it happen to fall on?
0.
Not 0. I think 1, right? And is it the first one to go in or the second one to go in? Second. Or is it pointing up or pointing down? It's pointing down, which means we are -1/2.